Well, we can start. Welcome back, everyone. We're doing the last class right before a big break, so I appreciate you all making it in. It's not always easy to do on these classes. As far as spring break goes, I'll still be available by email, so if you have questions, keep on sending them out. I'll be checking my email primarily in the mornings, but we won't be holding classes or office hours this whole week. However, it still makes for a great opportunity for getting caught up in the course. If you're behind on any of the quizzes, behind on any work in the MyLab homework system, it'll be a golden opportunity to get caught up. We'll have 6 more weeks to get through after spring break, so getting fully caught up will make the last 6 weeks a lot easier to get through. You'll be able to complete the semester going strong into finals. And for what we're doing today, we're going to be finishing off Unit 5C, Statistical Tables and Graphs. And then Unit 5D kind of goes along with it, except these are all pre-made graphs, and we'll just be analyzing them. And that's pretty much just going to be almost the completion of our work on statistics. They're kind of surface level work. We didn't go too deep into statistical methods. We're going to do one more unit looking into correlation and causality. Oh, Echo asks, will our finals be similar to the tests we've had so far? Yeah, absolutely. I'm glad you asked about that. We're getting closer to finals, so it's a good time to start talking about them. We'll get across an exam 3, then we'll have a week to kind of cool off after that third exam, and then we'll be into finals week. And pretty much the way I'm going to set up the finals is exactly the same way we did exams 1, 2, and 3. I'll put down a set of formulas that's going to be included on the exam. I'll include several review exams as well. Essentially, the way I write my final exams is I look over what did we actually do on exam 2, exam 1, and exam 3, and I'm going to take a selected questions from all of those, a representative sample, and that'll be our final exam. But you'll have the same kind of review documents, a couple versions for review problems as well. Version 1, it's going to be essentially the entire lecture notes all put together as worksheets. And version 2 is going to be all of the problems that we created new. As far as the set of notes, that's a pretty good question. We did 1 page of notes for every one of those exams. But I think for our final exam, because it's going to be a completely comprehensive exam, I'll allow for 2 pages of notes. Same size, front and back, handwritten or typed. And because you asked that, let me make sure that I don't forget I said that. It's awful to say something and then completely go back on it. But let's make that official. There'll be 2 pages of notes allowed on the final exam. And really compiling those notes is one of the better things you can do to study for any exam, really. That should be your first step you take after getting caught up on the material. Start putting together your pages of notes. You'll be well informed on just what kind of problems are going to be on the actual exam itself as we get closer and closer to the final exam. And that'll be really great preparation. Other questions at the moment? Okay, and maybe another comment to go along with the final. Another thing we're going to be doing, let's take a look at what we said in the syllabus. We haven't opened this up in a little while. As far as the schedule goes, as we get closer and closer to finals week, our goal is to review on 2 whole days. So we'll be finalizing the last unit where we get to in the course, and then having 2 review days altogether. So that's going to be our goal for finals week. I'm going to set up the final exam pretty much the same way, where when we come, well, first thing on Monday, what I'm going to do is email everyone in the course instructions for scheduling your final exam. It'll be open to be scheduled between the days of Monday, this is all the way over on the 4th of May, through Thursday, the 7th of May. So pretty much it's going to feel like just another run of the exam, another run of exam 1 through 3. Final exam is going to be formality. It is a 2-hour exam, but I'm not necessarily going to make it twice the length of exams 1, 2, or 3. It'll be pretty well contained. And again, it's going to be just a rough selection of topics that are representative over the sections we've covered. Amy says, so the final include 12A and B, which won't be on the third exam. Yeah, that's right. Anything that we don't get to, or excuse me, any topics that we cover after exam 3 will be included on the final exam. And so that possibly is something where we'll start the review just discussing good exam questions on any of the units that we cover after exam 3. So yeah, that's correct. The final exam will be comprehensive, covering all the units that we got through in the semester. Other questions at the moment? Okay, those are really great questions once again. We're here in the schedule, but finals week is going to feel like it comes fast. It'll be 6 weeks after spring break that we're getting through. And so far, now that we're looking at the schedule, I am behind a little bit. The unit on statistics, it took a little bit more time. In particular, 5A, I think that took like 2.5 days to get through. But it's a tentative schedule, so we may not get through all the topics listed here. We'll make sure that we end strong on whichever topics we get through. So we'll know exactly what the coverage will be once we get down here on the final exam, because it'll be essentially the last topics that we complete on Monday of this week right here is going to be the cutoff for the content on that final exam. Then the last 2 days on this week will be just purely for review. Again, those are really good questions. The final is coming up. It's out there 6 weeks from now, essentially. Well, 6 weeks after spring break. But other questions at all before we get started today? Okay, well, let's jump back into our unit on statistical tables and graphs. We started off thinking about tables, thinking about types of variables, and now we're ending the section on doing some graphs. We've done one already for categorical data, and we got set up starting on this one here for quantitative data. The context here is we're discussing soil amendments, not quite fertilizers, but other materials that can be added into the soil to give some positive effects on anything that's growing. And what we're growing here is heritage green gauge plum trees, so pretty specific. We're studying the effects of a new soil amendment. They didn't tell us what it was in this context, so we're thinking it could be something like a peat moss. That is a possibility. What they did was at the end of the harvest, they measured how much each one of these plum trees yielded in terms of the plum fruit in kilograms. So any one of these rows in the table here would say, for example, 14 different trees yielded between 70 and 79 kilograms of plums. So we really have a lot of data, and these data have already been summarized, binned into these categories. So it's a little bit different from the problem that was a couple above. Here we had the actual raw data, and then we put it into a graph like this. And from this graph, we could have created a histogram. But now we're jumping right into that step. All the data has been binned according to these bin widths of 10, going from 50 to 59 kilograms and so on. This tells us the frequency, the number of trees in each one of these new created categories. And when we go to create the histogram, we gave it the title. This is the yield of green gauge plum trees under a soil amendment they're studying. I like this axis, the soil yield in kilograms. It took all these bins and just laid them out, going from least to greatest using the ordinary ordering of the number line. And taking a second look, I'm okay with putting down frequency. It's what we did on the last example, but I had kind of second thoughts on that. I'll accept frequency for sure, because that's exactly what this is. But I think this chart is going to look a little bit nicer if we call it, say, what the frequency is in the first place. Number of trees. And we could have done that in the last problem as well. On the last problem, we went frequency, and let's stick with it on this one just to convey that's fine. That would give us full credit. But if we wanted to make it slightly more descriptive, we could have said, say, number of moons instead, because that's what each one of these bar charts corresponds to. And we kind of know that that's what's going on when it says moons of the outer planets. But being a little bit more descriptive, I think that would have been a better way to format that table. But just to convey frequency is fine. Let's leave it on that one. And revise to number of trees, just being slightly more descriptive on this display here for the histogram. Then the next thing we do is we just go along every one of these categories. It's almost as if we're creating a bar chart, but the only difference in the histogram is there is no gap between these widths unless data is missing. So on the 50 to 59 kilograms of plums yield, there was 2 trees. So we put a bar that goes like this to start off. Then in a bona fide histogram, no gap in the next category between 60 and 69. We have 60 to 70, but we're thinking height 8 is specifically in that range there. So we go up to a height of 8. And here's the next bar, the next rectangle in the histogram. So now this conveys there were 2 trees between 50 and 60. Notice a little bit is lost in the translation for sure, right at that boundary. You can't tell unless you look into the table, it was really specifically between 50 and 59. So if we're reading the table, we're looking between 50 and 60. And so there's a little bit lost in the translation when we put things right next to each other in this kind of way. So next category, we're up to height 14. So we create another rectangle. Right up to that height, drop it down. These are meant to be perfect rectangles, but it's a by hand drawing, so you don't have to be an artist or have the world's most steady hand. Mine looks a little bit wavy, but we'll leave it on paper to say that qualifies. Then we just keep on going down the line. So next one's at height 10. There are 10 trees yielding between 80, 89 kilograms. So that's roughly at this height. Let me try to draw these a little bit better. Another thing that's an important consideration is there's a definite area principle when it comes to these kind of graphics where if I accidentally made this width way longer for some weird reason, this would have had a lot more area. So we're trying to keep the width between each of the tick marks to the best of our by hand drawing ability as close to equal as possible to not emphasize one category over the other. So next, between 90 and 99, it drops off quite a bit, just 4 trees in that range. And finally, just 1 tree in the range between 100 and 109. So 1 tree, this one's going to be kind of hard to draw. This is kind of compressed, so go halfway here. Maybe about like that might do the job. So there's our histogram. It's pretty similar to what we drew with the box plot. Only difference is if we're dealing with quantitative data, we have this ordinary ordering of the number line, and so we just compress all the bars next to each other. Whereas for these, there's no number line here. We just put in an artificial order. We just decide to put in bars in descending order. But it's a completely fine plot if you did bars in ascending order. Or you could be just kind of an adventurous person and put them in whichever order you would like. Maybe Mars comes first and then Neptune and so on. The order here was kind of artificial in a certain sense. But not in this case. The category 50 to 59 absolutely comes before the category 60 to 69 and so on down the line. Well, we got through the first part of the problem. The histogram is now down on paper. All it's doing is taking the raw data, which was summarized into a frequency table, and this is a nice summary. But now the data is visual, we can get a better idea of what really was going on with that soil amendment. Any questions at all, folks, on getting to this part of the problem? Okay, now that we got to here, this is the tricky part of the problem. It's a little bit more subjective. We want to say something about these data using the context and the shape of the histogram that we got. And as far as the shape goes, notice it has one major peak between 70 and 80. And then it falls off about the same to the left and to the right, but it trails off a little bit more to the right. There's that one tree that's a little bit further off. Not exactly an outlier, it's still close to the main grouping of data, but we still have to say something about the data we see here. It's pretty subjective. So anything you say that's correct based on this display, uses the context, would get full credit. Any volunteers for anything to say about this display here? It's kind of tough to get started on these kind of totally open questions in a certain sense, right? One thing you might think about when you're trying to answer a question like this one, well, first of all, if you're doing it in MyLab, it's way easier because they give you multiple choice. And so you're just looking at which thing is the best description, which descriptions don't make sense. Maybe they're saying something with the wrong titles. Maybe they're saying there's a certain amount of categories, but the numbering is wrong, something along those lines. But doing it as a problem like this, it's extremely open-ended, right? This is about what a quiz problem or an exam problem would look like. And a good starting point for a question like this, what does the shape of the distribution suggest? About consistency of fruit yield across the orchard, we could say, well, where are most of the trees? Most of the trees go between 60 and 90. Or you could focus on the main peak. Most of the trees, or the highest category, is between 70 and 80. I'd probably go between saying most of the trees are between this range. Let's begin by saying most trees yielded between 60 to 90 kilograms of plums under this soil amendment. So that's one sentence in. This question didn't say write 2 or 3 or 5 complete sentences. It didn't say mention 3 items or anything along those lines. So it's actually kind of a brief thing that you could put down and it would give full credit. But other things you might say along those lines are, this is where most of the data is aggregated in the sense that that's where the main peak is. So you could say that the average yield is approximately, it's not going to be exactly at 75. That's going to be somewhere in this region. It's a little bit trailing off to the right, and it actually pulls the average to the right. And also, we can't calculate the average directly because we don't even have the raw data. But this histogram tells us about where it is, the central value, where all the data seems to be accumulating around the most. Either you could call it the average or the median. We'll say the average is approximately, let's just call it 75 kilograms. So that'd be another thing that you could mention that's worthwhile. We kind of said where most of the observations are. They lie in this range, so it's spread out in that sense. Most observations between 60 and 90. So we mentioned how spread out it is. And this statement is saying where the center is, where all the observations tend to accumulate, is around 75. If you see anything else that's kind of unusual, like for example, if for some reason there's a bunch of trees out here, that would be really weird in these data. These would be extreme outliers. That'd be something to definitely mention. Or if it takes on some other peculiar shape, if it takes on a shape that goes like this. This would be pretty weird as well. It would have a staircase, kind of a skewed pattern to the data. That would tell us most of the trees are yielding them towards the low end, And then it gradually goes down where some trees yield high and most of the trees are yielding low. But it went different on this experiment. There's a central value and it kind of fell off about the same in both directions. Well, any last questions or comments at all, folks, on getting through this display? Okay, well, we're through two different kind of displays already. We first looked into, if the data is categorical, how to create the bar graph or bar chart, if you prefer to say it that way. And this is about what it would look like. Histogram is also pretty similar, except you don't have category names. You just have a number line essentially going this way. Then you compress together all of the bins, and now it's a bona fide histogram. But there's a lot of other interesting displays that we're going to take a look into, not just in this unit, in the next unit, and the one right after that, the one that ends chapter 5. So here's going to be our last piece of data to take a look into. This is some interesting real world data on the, I might be pronouncing this wrong, but let's go for it anyway. The Mauna Loa Observatory. This is located on a high volcano in Hawaii. And this is a really important observatory because it's away from other kind of background air, anything that's going to contaminate the kind of measurements they're going to make in this location. It's extremely remote, extremely high altitude, so free from local pollution sources. That's the thought. And this one observatory has been continuously monitoring atmospheric carbon dioxide since 1958. So pretty long running set of data from this location. We're told the data collected here forms the famous Keeling curve that you might have read elsewhere, which is a critical piece of evidence in earth and climate sciences. So here's a snippet of their data. This is data that gives us a summary on a decade by decade basis, going from 1960 to 2020. It says the table shows the average global atmospheric carbon dioxide concentration measured in parts per million, abbreviated to ppm here. And this is recorded at the observatory at the start of each decade. We'll construct a time series graph. So here's our new display to give for the data. And then we'll answer a follow-up question. What does the shape of the graph tell you about the rate of change in CO2 levels over this 60-year period? Well, it's a whole new display, a time series graph, but we start off in a kind of a similar way. We're going to make one axis be horizontal, another axis be vertical. But in a time series graph, there's one big requirement. Here, the horizontal axis is time itself. We're looking at the change of the quantitative variable, the CO2 level measurement, as time changes. So that's going to be our axis to have here. Let's give it a name. This is year. We're going to start it off in 1960. Let me see if I can make this look just a little bit nicer for the axis. So I'll make the first tick mark right here be 1960. Let me go sideways to try to fit this in better. Then we're going by the decade, so let's increment to 1970, 1980. Now we're in the 90s. Year 2000, 2010, and the most recent decade measurement, 2020. So here's our data so far. We also want a title. Let me see if I can move that down to plan for that better. So we can say for the title, this is CO2 levels measured in, let me scroll up to spell that correctly, Mauna Loa I really should have practiced pronouncing that before class today. Apologies. So there's our title going that way. And next, after we have the year, that's our major requirement for a time series graph. We take the quantitative variable. This time we don't have frequency whatsoever. This is just one measurement. There's no binning happening at all. So we're just putting CO2 level going this way. In parts per million. So our variable goes in this location. And we might as well mention that as well. Vertical axis is the quantitative variable. So now we have to decide on a good range for this quantitative variable. So we're going up to 400 altogether. And on this plot, we can say, let's go by, how about hundreds? That should do the job. If we're going by hundreds, we can say, let this be 0. That's not a firm requirement on a time graph. But if we start by 0, we could say that this is 100, 200, 300, and finally, well, I said finally 400, but let's go a little bit higher because we want to go beyond the maximum of the data. So even though it doesn't go quite as high as 500, at least this contains the data itself. Amy says, why would you not use the exact measurements? So you mean on the vertical tick marks right here?
Yes.
You know, you probably could. And I would say the major reason of just putting a scale down first is kind of along the lines of the reason of putting down a scale on this one as well. We definitely have a value of 146 that goes here on this one. But then when we go to put down the next height of exactly 95, if we started with an axis that looked like, say, this, say 146 on this one, it can be kind of tough to determine, well, where is the height exactly at for 95? It's hard to kind of place it on a scale unless we have already the tick mark structure to tell us where all these values are relative to where we place those tick marks. Putting a 95 once we have an exact height of 146 as our major tick mark, well, it'd be kind of tough in a way, right? I'd possibly guess maybe it's about here for a 95, and then guess the next one at 28. Maybe it's about here, but I'm actually looking at this graph right here. So if I went that route, I would say the only reason not going this route is it's just a little bit tougher to say exactly where the next heights lie relative to a value like this. However, if you put down, let's see if Control Z will bring it back. If you put down a scale like this first, uh-oh, hang on. Got an issue with Control Z. It might not come back to the way I wanted to, but you know, that's okay. We can resurrect it some way. Okay, let me see where it comes back as. It's being a little stubborn. I think Microsoft Word had a little bit of issue. It deleted the horizontal axis for some reason and the vertical axis. But the major idea is, I think if I recall correctly, we were going by 25s, landing at 150. If we have the scale down, it's easier to plug in these values because now we're just saying, where are each one of these values relative to specific tick marks? So let me recall if that was by 50s we were going by or 25s. think it was 25s, if I remember correctly. So that'd be 50, 75, 100. That's about right, I think. Maybe a little bit of a change there from what we had originally. But with all these down, it's a little bit easier to plug in the actual heights. Because now we can say 146, just shy of that tick mark. 95, just going to be below that tick mark. But using these values, it's hard to place them in a scale that's actually measurement that's uniform altogether. Does that kind of make sense with that question there?
It does, but I have another question now.
Yeah.
So this chart, it really goes from say 300 to 415, right? Do you have to start at zero, or could you not like use smaller increments to show more like a snapshot where you're showing clearly exactly where each one's at? Do you have to do it by hundreds? Do you know what I'm
No,
saying?
not at all. Yeah, absolutely. Yeah, starting at zero, that was just one particular choice I made, but let's think about the effect of that. If I start at zero, then the curve that I'm going to draw is going to kind of get compressed, and it may not actually show how big the change was going from 1960 to 2020. If we go from, say, 300 to maybe 425 and use finer tick marks, it's going to show the absolute change between here to here in a more magnified sense. So the omission or the inclusion of zero, it really just depends on what we're trying to focus on. And I would say for this particular problem, especially for scatter plots in general, which a time plot really is, it's a scatter plot of data, trying to stay within the variable is not a bad idea. So that would absolutely work on this problem. In fact, let's go for that graph. Let's start, say, at a minimum around 300 and then go up to, say, a maximum of around maybe 425. That would be a perfectly fine display as well. Does that make sense with that question there?
Yes, thank you very much.
Yeah, absolutely. And yeah, that's a great suggestion. If I stick to this graph, the story we tell, we might be skewed to a certain kind of opinion. It might look like there's not a lot of change really. But if we decide to go from, say, 300 and then up to just beyond 412, visually, the story is going to look a little bit different. We're going to really emphasize the decade by decade change a lot more. So this one didn't have any hard and fast rules, but for just like we mentioned before, a general idea with a scatter plot, which is what a time series graph is to just capture the range of the data, not necessarily trying to force in a zero. So let's go this route. Let's start at 300 and maybe go by 25s. This will be 325, 350, 375, 400, and just one more tick mark, 425. Now we've got all the tick marks. We can place the data within those bounds, and that's going to be our next step. Essentially, we're just putting down dots and connecting the dots on the next steps for completing this graph. But other questions or comments at the moment? Okay, let's see how this comes out as. 316.9 to start. That's going to be on the closer end of 325. So we're going to be, here's halfway, just a little bit higher. And that's our first dot. And again, we're doing this by hand, so it doesn't have to be perfect. Do your best visual estimate based on the scales you put down to place that dot. And that's essentially all we're doing. We're just plotting an x coordinate year against a y coordinate, the CO2 level. So on the next one for 1970, we're at 325.7. So that's right on the 325, slightly higher. Then it's creeping up, 338.7. So that's going to be close to 340. So roughly maybe about here. This one exceeds the 350 tick mark for 1990. So just a little bit higher than 350. And if you wanted to, you could add a little bit more to this graph and go horizontal dotted lines to just kind of make sure everything is right in scale. So if that's helpful, that's not a bad strategy to take. It has a trade-off. It adds a little bit of visual clutter, but it might give a little bit more accuracy on getting these heights just right, especially when the scale gets kind of long horizontally. So next, year 2000, we're almost at 370, so just shy of 375. So right around here, just a little bit lower. Then year 2010, 389. So 389.9, close to 390, right around here, year 2010. Finally, year 2020, we're at 412.2, and we'll have to wait a few more years before this extends to the next row. But that's pretty close to midway between 400, 425. So I'd place it about here. So there's the graph. And again, with the other design choice, starting at a 0, going up to 500, you take this whole set of dots, which we can now connect through a curve, trying to make it a nice smooth curve going through those points, and it would get compressed. Is it wrong? Not necessarily, but contextually, again, we might get a different story that we're going to tell from that versus this graph. This graph emphasizes the actual absolute change much better when we're constrained between the actual levels that were obtained. So there it is. This is the change in CO2 on a decade by decade basis from 1960 to the year 2000. All we now have to do is say something about this graph. Much like we did with the histogram, there's lots of different things you can say when it comes to a time series. Any volunteers for something you might say about this one? Yeah, there's as Echo said, a gradual rise from decade to decade. It's not turning around whatsoever. So that's definitely something we can mention. There is a increasing trend of higher and higher CO2 levels. So absolutely, there's a pretty interesting trend here. And if you really look closely on this curve, you might have noticed that the first 3 dots, and maybe even the first 2 dots, they would have had a particular shape if that's all we saw. So if we say covered up the graph and only looked at this part right here, maybe we can do that temporarily. Let's see if we can black this out. If this is all we saw, and we were drawing a curve and maybe thinking projected it out to the future, it's extrapolation, but we can now compare that with the actual data. If I drew a curve that went through here and it looked like that, this is the extrapolated CO2 levels. Now I'll bring the original graph back. Notice something kind of remarkable is happening. And maybe it got exaggerated. Maybe I kind of erred just right to exaggerate a curve here because it was by hand. But I bet if we made computer software plot this, we might still see this kind of effect. The curve is not just increasing linearly. This is increasing by the same amount every single year. It's accelerating. It's increasing how much it increases by each and every year. So we can also say this wouldn't be critical if we missed this observation. But when it says about the rate of change in CO2, this curve here against the actual data is telling us another story. The rate of increase, you could say, is increasing. That might feel kind of redundant. I think a lot of people would phrase it by saying the rate of increase of CO2 is, I think people would often say accelerating is a better word there. But if you said if the rate of increase is increasing, that's mathematically correct. That would work. I'll say is accelerating. Is it accelerating by a lot? Well, that's where we're going to have to be a climate scientist to really say for sure. But I would say this picture is pretty striking as well. And we're just looking into, as far as climate science, this is one variable in a sea of thousands of things that you have to keep in mind when you're talking about climate. But this is a pretty remarkable graph just all on its own. It's pretty reliable data from the observatory in this location right here. And again, that's just really our last display that we're taking a look into. We're going to look into more different kinds of displays that get a little bit harder to draw by hand. But drawing these out by hand is just a great way to think about what is the data trying to tell us once we're looking at it, because we built it ourselves. But any last questions or thoughts, folks, on finalizing this one? Okay, well, let's go off to the next unit. The next unit, we're going to look into a lot of different kinds of graphs. This one says, for a generic title, graphs in the media. Here we're combining lots of variables, categorical variables together with quantitative variables into lots of different kinds of now pretty visually overwhelming types of graphs. So the next skill that we're going to look into 5D is trying to look into what the information we see in the graph, what story is being told. We're going to look at a lot of different kinds of graphs. So the first one looked like it was about internet penetration in 2023. Next graph is kind of an interesting one, per pupil public school spending by state. Notice the graph is interesting. It doesn't start at 0. Then we're going to look at other things. We're going to loop in the CPI table and look at percent change on a year-by-year basis. So these are interesting data. The graphs kind of get more and more complicated. We'll look at net energy balance. So there's lots of variables here, interesting units, and color coding to go along with it. And then the challenge question, kind of going back to time series, will be the Idaho potato industry trends. This is a pretty complicated looking graph. We'll see what we can say about it and maybe produce better graphics than this one by hand. So that'll be the challenge question of the exercise set. But to get started, let's begin here. Example 1 says the accompanying figure shows global internet penetration, probably defined as how many people in the particular country are connected to the internet in countries around the world for year 2023. So it's definitely a graph, quite a lot different than the graphs that we did in the prior sections. This is not a time graph or a bar chart in any sense. We're looking into geographical data together with a measurement of internet penetration. So here are a bunch of countries color-coded. If we see this category here, 0 to 20%, that would mean 0 to 20% internet penetration. That's localized to these regions here. 21 to 40%, we see in regions like here in South America, other regions here in Africa, Greenland as well. And then it increases across these categories up into the higher levels, where we see countries like United States, Canada, Russia, Australia, and so on, various countries in Europe. So that's the story of the data so far. And part B are pretty similar questions. Part A asks, does the figure allow you to determine whether internet penetration is greater in the United States or in China? Why or why not? Well, this is probably not the best exam question ever because, I mean, we're not trying to test on the skill of geography. So it works better as a homework skill. But here's China, here's the United States. And based on that, United States is in this category, 81% to 100%. China is on the category 61% to 80%. We don't know where they are in that category. They could have been 79.999% for all we know, but we just know that they're in this category. That means we can determine this. We can say yes. We can determine internet penetration. That's a weird vocabulary way to say it. Internet penetration is greater in US since it is in the 81% to 100% category. And China is in the 61% to 81% category. So any questions at all, folks, on that conclusion there for part A? Okay, now part B, pretty much the same question. It asks, does the figure allow you to determine whether internet penetration is greater in the United States or Australia? Why or why not? Any volunteers for this one? Would you say yes or no to this?
I would say no because they are the same color, so we can't tell exactly where they fall.
Yeah, exactly. Let me put that down just as you said. Both United States and Australia are in the 81 to 100% category. And so we cannot determine which country has greater internet penetration. Again, kind of weird wording there. So yeah, that's pretty much the idea with this graph. Again, it's kind of visually overwhelming, but the longer we stare at it, the more we kind of understand the story it's trying to tell. What they did was a lot of data was pulled into this. There's so much data that to really kind of summarize it, this is the display we got. But a lot's lost when we make a display like this. We can't answer a question like part B whatsoever. We have to go back into the raw data, find out the internet penetration rates in the US, find out the exact rate in Australia, and then we can answer. So it's both a useful graph, but there's limits to how useful it can be depending on what we're trying to ask and answer. And for a couple more follow-up questions, let me put the graph down below so we're not scrolling up and down a whole bunch. Part C asks the question, or starts off by saying, global telecommunications data estimates that the worldwide average internet penetration in 2023 was roughly 67%. So in that year, on the whole planet, we're at 67% based on estimates. Now it asks the question, are the internet penetration rates in Brazil, China, above, at, or below the global average being that 67%? So let's think about this question so far. It's a lot going on. We're looking into countries, Brazil and China specifically. We're wondering if we compare it against the global average of 67 internet penetration, Are these countries above, at, or below the global average? This question is weird, but we can explain our reasoning and still be okay on this question. Anyone notice the kind of problem with the way the question's posed in the first place?
We don't know because they said 67 was the average and the range for both Brazil and China run between 61 and 80%. We don't know specifically if it is at average or above or below.
Yeah, exactly. This one is kind of a misleading question in a real sense. This would be a bad exam question. I think I would try to make the question a little bit better worded because it makes it seem like we can answer it either above, at, or below, but it's actually none of the above. So to fix this question to make it a good exam one, I would have to say at, above, or below, or neither to include that possibility. And like you said, it's neither. If the average is 67%, like you said, but both countries are in this category, it's conceivable that they could be one or the other or both right at 67%, or they could be above or below. There's just not enough information to answer. So let's say it that way. There is not enough information to answer because that 67% figure is in the range of 61% to 80%, for which both countries belong to. So in other words, when we're saying not enough information, we mean either Brazil or China could be above, below, equal to 67%, one or the other. We just can't answer that whatsoever. It's a nice graph. It shows us what's going on as a nice snapshot in 2023, but definitely not enough information to ask a targeted question like this one. If we were talking about, say, maybe Greenland or maybe India, we would say they're below because those are in categories 41 to 60%. And the average was slightly higher. So we could give a definite answer to that. But question 6 was kind of roughly misleading in this certain sense. But as long as we explain our reasoning, we can still get through this kind of question. Again, I'll try to not make a misleading question like this one on an exam setting. I think that would be kind of rough. I try to make the exam questions a little bit more direct. As far as homework questions on my lab, stuff like this can absolutely come up. Well, one more to get through. Part D says, in the year 2005, the global average internet penetration was roughly 16%. Going from 67 to 16 is pretty stark. But if all we're looking at is, say, just this graph down below, it asks, how do the highest internet penetration values by country today compared to the average in 2005? Again, that's kind of a remarkable figure. That's just 21 years ago, and a lot has changed. One way to answer this question is, imagine that we had not just one graph like this, but an entire slideshow of different graphs, years winding back year by year by year until we hit 2005, same exact categories, and all these colors are going to change by a lot in some of these countries. If the average internet penetration was 16%, then we can say the graph, meaning like the one we see below, for 2005 would have, they said it was an average, so I would say approximately half of the countries in, well, 16% goes in this range. And if that's the average, we're expecting half of the countries in the 0 to 20% range. Again, imagine what the coloring of that graph would look like. It'd be starkly different. But in 2023, there's 1, 2, 3, 4, 5, looks like 6 countries. It's kind of hard to see because the graphics get kind of compressed with some of the smaller countries. But in, let's say here, but in 2023, there are only about, because it's kind of hard to visually estimate these borders, we could have potentially missed an island or something, but there's only about 6 countries in this range. So the question was asking, how do the highest internet penetration values by country today compare to the average of 2005? Well, we can directly say now to answer that high penetration values rapidly became common in 2023. There was just a massive surge in internet penetration from the year in question, 2005, to the year we're studying in 2023. Pretty impressive altogether. But any last questions or thoughts, folks, that you'd want to add on to that so far? Okay, again, it's a tricky graph because it's just visually busy. We're looking at geography at the same time as there's a quantitative variable along with the categorical variable of countries, but the quantitative variable is now color coded. So there's just a lot going on in answering these kind of questions. And for the next graph, it's going to be quite a lot different. We're returning to a standard bar graph to take a look into. But still, there's quite a bit going on with these data as well. And this is some pretty interesting data as well. This is the bar graph that displays the per pupil public school spending for 17 selected states. Most of these are states nearby Idaho, but there's some one-offs. Like I think there's a Mississippi and Alabama here for no apparent reason. I just thought it was interesting to include them. But mostly we're thinking about the West Coast, nearby Idaho. This is 2025 data for those 17 states. So it's a bar chart, and this one's going in the ascending order. We have the categories of the different states and the spending per student amount for those states, going from $8,000 spent per pupil up to $25,000, California being just shy of that value. But when you look at this display, anything that you would say might be a red flag by seeing that kind of picture? This one will be kind of interesting to break down. So one thing that's kind of weird about this is the data isn't wrong. There's no problem with that. It's arranged in ascending order, showing Idaho dead last. That's for sure. Kind of, that kind of hurts a little bit, but it's Idaho is dead last in the amount they spend per pupil in public school. But another thing that's really weird about this is if you're comparing Idaho to, say, Oregon, like we're going to do in part A, here's Oregon. Oregon's bar is this high. That looks like it's about 10 times as big as Idaho. That's not telling a very honest story though, because the actual per pupil public spending in Oregon is not 10 times the amount spent in Idaho. Not even close. It's definitely more. But this graph is exaggerating the change way too much. This graph is actually very, very dishonest, which is in stark contrast when we looked into the time plot. In the time plot, excluding zero is probably a good idea because we're trying to show the change. But here, we are overemphasizing that, say, California is being something like 15 times more in spending when it really isn't. So we're going to break down this table, show what the ratio is for Oregon spending to Idaho, not as bad as it seems here. Look at what the actual heights is really telling us to get a good story of, or a good idea of what's wrong with this display. And it's kind of tragic because this is really important data. If someone was trying to present this in, say, Boise to the state senate to try to increase extra spending, but one person points out this is a flawed graph, that we're being dishonest, then people might not go along with the argument that you're trying to provide just because there's dishonesty in the graph. That might be enough for people to shut us all down. So there's important data that we're going to look into here. Idaho needs a little bit of help based off this graph. But the first thing we need to do is give an honest graph. Idaho is not actually that bad. Well, it's going to take some time to get through this problem, and I feel like running right to the last minute, rushing through important real data like this is kind of cruel and unusual right before spring break. So I think this will be a good stopping point for us today, ending a good amount early, but we've been working hard all semester. Any last thoughts or comments with what we've done so far before we call it a night? Okay, well, when we come back from the break, Monday on, this is going to be towards the end of March, the 30th. It'll be a little while. We'll refresh on what's going on with this display and just see how misleading it really is. But also be honest that Idaho is still not doing great. Then we'll look into other matters like what's going on with the CPI here from years 2004 to 2025. This will be a fun one because it's based off the same CPI table that we dealt with back in chapter 3. Then we'll get into other charts like the energy balance and go back to Idaho. We have to end on a good potato problem for analyzing data. And then that'll take us into the next section. So we'll end here a little bit earlier than normal for tonight. Thanks for your hard work and appreciate you all making it in right before the break. That's tough to do sometimes. Have a great break, folks. Try not to work too hard, and I'll see you all on the 30th. Take care. Thanks, you too. Oh, gotcha. Well, if you're not able to attend Zoom on that week after spring break, and first of all, that sounds like an awesome vacation. Glad you're able to make that trip. But I'll still have the lectures recorded, so you can make up the work and the lectures once you get access to internet. So you won't be docked any points or anything along those lines if you can't make it into Zoom due to internet access issues.
Okay, thank you.
Yep, you bet. And yeah, have a good trip. That sounds like awesome, awesome time.